How do you determine specific heat? What you can do is you can mix something hot and something cold in an insulated container called a calorimeter. So here's a picture of a calorimeter. Okay, this is an experiment where you put water inside. So you have water inside. And in here you have your sample, like maybe a piece of metal. So here's your sample, okay, at a different temperature. Okay, you mix the two. Okay, so in a calorimeter, you have an insulated apparatus for measuring heat measurements. So because the calorimeter is insulated, Q must be equal to 0 inside the calorimeter. So Q for everything going on inside your calorimeter plus, okay, you have C cal delta T cal must be 0. What is this C cal times delta T cal? This C cal right here is the calorimeter constant. That's actually, okay, you mix two things, but then you're not really just having those two things in there, because in addition to the two things that you're mixing, you got the immediate surroundings, which would be the air above your sample, okay, the walls of the calorimeter, and there's a thermometer that you have in there, there's a stirrer that you use to mix the two things that you're putting together. So all of those extra stuff in there will absorb some of the heat or will release some of the heat depending on what's going on. So the we, we, we lump all the heat capacity of all of these things into just one value. So you call that the calorimeter constant. Okay? So your delta T cal would be the change in the temperature of all of these other things. So how do we do this? Okay, let's illustrate that with a problem. You have a 70-gram sample of metal, okay, with a specific heat of 0.3 joules per Kelvin per gram at 100 degrees. So you have a hot piece of metal, 100 degrees, okay? You pour it into a calorimeter that has 100 grams of water at room temperature of 20 degrees. What happens? The water gets warmer. It becomes temperature, final temperature of the whole thing becomes 23 degrees Celsius. So the metal, which used to be 100 degrees, is now at 23 degrees. The water, which used to be at 20 degrees, is now at 23 degrees. So you know the specific heat of water, you know the specific heat of the metal, you can figure out the calorimeter constant. The way you do this is you say Q of the metal, okay, plus Q of the water plus Q of the calorimeter must be equal to 0. Okay? What's Q of the metal? Mass of the metal times specific heat of the metal times delta T for the metal. What's Q of the water? Mass of the water, specific heat of the water times delta T of the water. And what's Q cal? The calorimeter constant times delta T for the calorimeter. What's delta T for the calorimeter? That's the same as the delta T for the water, because initially you have your water in your calorimeter. So this delta T for the water is the same as the delta T for the calorimeter. And you know all your delta T's, you know all your masses, you know your specific heats. What's the only unknown here? This one is your unknown, okay? And so this whole thing is equal to 0. How do you solve for your unknown? You move all of this to one side and then divide by that, right? So you say C cal, the calorimeter constant, would be equal to negative of Q metal minus Q water. Okay, this is Q metal, that's Q water. You move it to the other side, divided by delta T cal. Right? So what's our Q metal? Mass of the metal is how much? C of the metal is how much? Delta T for the metal is how much? Q of the metal. Okay. Mass of the metal is 70 grams. Okay. 70.0 grams. What's the specific heat of the metal? 0.300 joules per Kelvin per gram. Okay, let me put those units in. Joules per Kelvin per gram. So gram cancels out. And what's the delta T for the metal? Negative 77. It went from 100 to 23, right? So 23 is the final minus the initial, which is 100. So this would be negative 77.00. Negative 7. Sorry, negative 77.0 Kelvin. So Kelvin cancels out. So that's Q for the metal. And don't forget, we need to put a negative here, right? Okay. So that's negative of Q metal. And then minus Q of the water. What's Q of the water? Mass of the water is how much? 100 grams. Specific heat of the water, you should know, is 4.18, okay, joules per Kelvin per gram. So gram cancels out. And delta T for the water. How much did the water change? From 20 to 23 degrees Celsius. So that's 3.0, right? So 3.0 Kelvin. That cancels out. And then you divide the whole thing by delta T cal, which is what? What's delta T cal? The same as delta T for the water. So divided by 3.0 Kelvin. Okay, let's look at some numbers here. What are these numbers? So that's negative of Q metal. What's our Q metal? 1,000. Negative 1,617 joules. Why negative? The metal was hot, it got cold. So heat flow, we say there was a heat flow out of the metal. Okay? Minus Q of water is how much? 1,254 joules. Positive, right? Why positive? The water absorbed heat. So 1,600 went out of the metal, okay? But only 1,200 went to the water. Where did the rest of it go? The rest of the calorimeter, the stirrer, the thermometer, the air above it, in the immediate surroundings, okay? So that's the amount of heat that did not transfer from the metal to the water. So this difference right here. And so you divide this one by delta T, which is 3.0 Kelvin. What do you get now? Okay, let's look at our sig figs. This should have 3 sig figs, right? And this one should only have 2 sig figs. But we'll keep those extra numbers just for safety. You don't want to build up round of errors. So what do you get? 1617. Negative, negative, that's plus, right? 1617 minus 1254. That difference of 363, okay, joules is the amount of energy that did not transfer from the metal to the water. It went to the rest of the calorimeter. Divided by 3.0 Kelvin, okay. So what would this be? 363 divided by 3. 121 joules per Kelvin. Okay. Now, how many sig figs should we have here? If we go by the sig fig rules, Okay, this the last sig fig there is in the hundreds, the last sig fig there is in the tens, so we really should have just sig figs in the hundreds. So there's really only one sig fig here. Okay, so only one sig fig left. So it's about 100 joules per Kelvin. But usually when you determine the calorimeter constant, you're going to be using it for further calculations. Okay, the calorimeter constant is just a way for you to calibrate your calorimeter. So now, once you've calibrated it, you can use it to determine the heat capacity of an unknown substance. So what we're doing here when we're determining the calorimeter constant is we're calibrating our calorimeter. We're checking it out using known quantities. So two known substances with known heat capacities, known amounts. Okay, so we can figure out how well that calorimeter handles the heat transfer. Okay, so although you should only have one sig fig here, usually we keep extra digits there because we're going to be carrying over that number to another calculation. All right. So here's an example of a follow-up to that. In this case, now you have a calorimeter that you have calibrated, so you know your calorimeter constant is 125 joules per Kelvin. Okay, so this time you mix a 150 gram sample of a metal, unknown sample. Now you don't know your heat capacity. You're being asked for the specific heat of the metal. Okay, so this is now your unknown run. And then you pour in a calorimeter containing 100 grams of water at 20 degrees. So your metal again is hot, your water is hot. You know how much heat your water is going to absorb. You can calculate it, right? But as far as your metal is concerned, the specific heat is unknown. So what should we do? You say Q metal plus Q water plus Q cal is equal to 0, right? It's a basic equation in calorimetry. All the Q's add up to 0 because in calorimetry, your calorimeter is insulated. So what is C cal? It's Q cal is C cal times delta T cal. What's Q water? Mass of water times specific heat of water times delta T of your water. What's your Q metal? Mass of the metal times specific heat of the metal times delta T of your metal. Okay? All of that should add up to 0. What's my unknown here? I know my delta T cal. What's my delta T cal? It went from 20 degrees to 24.5. So this is 4.5 degrees Celsius, right? C cal, I know, is how much? 125 joules per degree Celsius or joules per Kelvin. So I know that. Delta T for the water is 4.5. It started out at, okay, let's call that Kelvin instead of Celsius for consistency. It went from 20 degrees Celsius to 24.5. Specific heat of water, do we know? 4.18 joules per gram per Kelvin. Do we know the mass of the water? The mass of the water was 100 grams, right? Do you know delta T for the metal? The metal started off at 100 degrees and it ended up at 24.5. So what's delta T for the metal? Negative 75.5. Keep that in mind, that's negative, okay? Do you know the mass of the metal? 150 grams, right? So what's the only unknown here? The specific heat of the metal. So you have all the information you need to solve for the specific heat of the metal. So I'm not going to go into the details of that calculation. You should be able to work it out, okay? All right. So let's summarize the procedure for determining specific heat. You do a standard run, right? You mix two known things. Usually one of them would be water, and then the other one would be some other known metal, okay? You look up the specific heat of the known material. So calculate Q water, Q known, and Q is mass times specific heat times delta T. Then you can calculate Q cal, given that all of those Q's should add up to 0. And then from that, you can calculate the calorimeter constant is just equal, given that Q cal is C cal over delta T. So that was the first example we had. And then the follow-up question was one where we had an unknown run. Okay. Now, sometimes, oftentimes, in fact, in textbooks, they give you problems for determining specific heat. And in those cases, oftentimes you are asked, you have to make the assumption that Qcal is 0. So if you don't have information about the calorimeter constant, if you're given a problem, just assume it's 0.